Thank you. I'm going to talk about the work that I did as a part of my graduate school study. So the focus is on wavelength dispersion of Verdet constant in electric field-oriented iron oxide doped polymer nanocomposites. So the driving force behind this research was that we wanted to develop a cheap magneto-optic sensor, but we didn't want to compromise on the sensitivity. So we focused on high sensitivity with the chosen material. And I'm also going to describe the process method that we used in this particular sensor development. So some of the applications of these magneto-optic sensors are in like optical current transducers and transformers, military applications for magneto-optic imaging, optical drives with higher storage density. You can also have them to function as current control signal isolators, and optical fiber-based signal switchers and modulators, and laser characterization and tuning. And also, this is going to be like way in the future, quantum computing, where you can develop magneto-optical traps. So the materials that we chose for this particular study, we used a thermosetting polymer, phenyl methyl vinyl siloxane, poly-phenyl methyl vinyl siloxane, and this is an optical quality thermosetting polymer with a refractive index of 1.53, close to glass. And for the nanoparticles, because we're developing a magneto-optic sensor, we wanted to go with some composite of iron oxide, some compound of iron. So we decided to go with hematite and maghemite. They both have ferromagnetic and ferimagnetic characteristics, but that will not be focused in the scope of this presentation. For the composite fabrication, we used a control sample, and in addition to that, we also used the nanocomposite, where we doped it with concentrations from 0.03% and 0.06% of the iron oxide. We didn't want to compromise on the optical clarity, hence those particular numbers. They are arbitrary. So the composite was sonicated for 12 hours to get like a uniform dispersion, and we filtered it using 0.45 micron filters, and the final composite was polished using diamond aerosols. Now, one thing that we did for this particular development was we used an electric field to orient the nanoparticles in the polymer before it was thermoset. That way, we wanted to test if there's some sort of a tuning in the optical clarity of the sample. The image on the side shows how an electric field oriented sample looks and how a plain doped sample without having any sort of electric field orientation looks. Now, both those images are taken from a sample with the same concentration, the one above with an electric field orientation, the one below does not have one. So the theory that we've employed in the development of these sensors, Faraday rotation, where we study the electric field rotation of plane polarized light under a parallelly applied magnetic field, where theta F is called the Faraday rotation angle. It's directly proportional to the magnetic permeability of the medium, the magnetic field strength applied, the length of the sample, and the V there stands for the Verdet constant, which is basically the constant of proportionality. And the wavelength dispersion of the Verdet constant is given by Henry Becquerel's formulation, where V equals gamma times Q over 2mc times lambda times dn over d lambda. Gamma is a factor called the magneto-optic anomaly, which differentiates or rather compensates for theoretical and practical differences in measurements. And dn over d lambda is the chromatic dispersion factor for the sensor that we're developing. So the electric field orientation of these nanoparticles. Now, we performed the mathematical modeling of how the electric field acting on this particular composite would move around the nanoparticle inside the polymer matrix. So there's going to be a torque that's acting on the nanoparticle due to the applied electric field, and we computed the relation between electric field based orientation and how it affects the Faraday rotation angle of the whole composite itself. So the nanoparticles that we used in this particular study, they're confocal ellipsoids with an aspect ratio of 3:1, and we performed like a boundary value assessment of the electric potential acting on this particular nanoparticle, and we were able to come up with what is going to be the ensemble electric field applied to the whole material composite. So I'll rush through this equation because it's going to be too descriptive. And finally, the torque that's going to be applied to the nanoparticle, thereby orienting these nanoparticles inside the polymer matrix, is going to be maximum at an orientation angle of 45 degrees. Now, this plot shows you a theoretical model of what kind of electric fields we could expect to orient the nanoparticles, and the 4 red markers there are the ones that I've chosen for this particular study. So I chose electric fields ranging from 2.5 all the way to 6.25. For the optical measurement, the Verdet constant itself, we used a Faraday effect-based optical setup. So we have a light source, a polarizer, and a Wollaston prism for the polarizing components. And the sample is placed in the middle of a Helmholtz coil, which is going to be generating a parallel magnetic field. And then we have all the lock-in mechanisms and the data acquisition system. Now for the material characterization, we characterize this particular material using small angle X-ray scattering and transmission electron microscopy. So figure A is actually showing you how the sample looks when there's absolutely no orientation. Now figure B is where we're looking at a sample where the nanoparticles have been oriented. There's an electron diffraction pattern showing that the material is, we're not looking at some striations or some bad formations in the polymer, but rather we're looking at the exact material. And figure C shows that the nanoparticles that we've used in certain cases have dissociated into quantum dots in the polymer matrix itself. Now, for the small angle X-ray scattering, we focused on 2 theta angles between 0.1 and 0.5 degrees because of the large sizes of the nanoparticles that we used in the study. Anything beyond 0.5 degrees was basically noise. So, with increasing applied electric fields, we noticed that the scattering intensity increased up to a point, and after a point it just came down. So at up to 5 kilovolts per centimeter, we noticed that the scattering intensities increased, and at about 6.25 kilovolts per centimeter, the scattering intensities came down. We tried electric fields up to 7.25 kilovolts, and at 7.1 kilovolts, we had an electrical breakdown of the system of the composite itself. Now, for the results, we tested the Verdet constant at 4 different wavelengths, 405 nanometers, 473 nanometers, 532, and 632.8. The main reason we did this was we wanted to gauge the potential of this material as a free space isolator or a Faraday isolator, to be to name another moniker. So the magneto-optic anomaly, we computed it based on the control sample where we did not have any dopant, and we looked at how different different dopants and different doping concentrations with different electric fields worked on this. So that's the Becquerel equation again. Now, when we looked at the first set of samples that were doped with hematite and poly-phenyl methyl vinyl siloxane, we looked at the wavelength dispersion of this particular constant, the Verdet constant, and we noticed that for electric fields of 2.5 kilovolts and 3.75 kilovolts, at around 530 nanometers, we were able to get like a peak Verdet constant, and anything beyond that, the Verdet constant just kept decreasing. So for the 0.03% hematite, the Verdet constant was measured at about 7.9 degrees per Tesla centimeter, and the 0.06% hematite dope sample showed 3.03 at 632.8 nanometers. That was like a linear shift. I mean, it came down by half almost. The enhancement is like basically because of an optical wavelength, an optimal wavelength at 632.8 nanometers, corresponding to the frequencies that we were measuring at. And the resonant energies for hematite is about 2.2 electron volts, and compared to that, the wavelength at which we could observe a maximum Verdet constant was around 530 nanometers. And when we looked at how much the enhancement was in terms of the Verdet constant, it was about 33 to 44% across all these wavelength frequencies. Similarly, for maghemite, we had Verdet constants at about 4 degrees per Tesla centimeter and about 2.7, and that was at 632.8 nanometers. Now, this one has a resonant energy at about 1.9 electron volts, so we had it closer to the 600 nanometer range. Now, in summary, we found out that the dopants that we used changed the chromatic dispersion factor, and they were linearly affecting the Verdet constant in accordance with Henry Becquerel's equation. In addition, the electric field-based orientation of these nanoparticles, it tunes the optical clarity and birefringence of the sample. Now, this has been substantiated, and more evidence is given in one of my other papers, which are not included in this study. And the Verdet constant, it increases as the incident photon energies have more proximity towards the resonant energies. And like I mentioned, for hematite it was about 2.2 electron volts, and for maghemite it was about 1.9 electron volts. Now, if somebody is curious as to how is it that I could call them as quantum dots, they have a Bohr radius of about 24 nanometers, And if you look at the sizes of the nanoparticles that I showed before, they were in the range of 50 to 60 nanometers. It's highly possible that they showed like a weak quantum confinement effect. And we did have particles lesser than 24 nanometers that we noted in the study, so which is one of the main reasons that we are stating this. And the main purpose was classification of this material for optical free space isolators, which we were able to find out as a part of this fundamental study. And that's it. I'll be happy